Assalamualaikum and a very good morning. We are from Group 4, me Nurul Aliah, and with my fellow friend Najihah and also Faqehah Sofeeyah, we're going to present about the Project 1 FIR filter design using high-level synthesis. The main objective of this project is to filter a 10 MHz sine wave that has to sample at 50 MHz and contaminate with additive white Gaussian noise, and then we're going to compare the performance of this filter using three platforms, which is the Python, the C++, and also the FGPA RTL. We have 5 tasks that we need to do. The first one is the Python, the second one is the C++, the third one is the -ls. The fourth and fifth task will be presented together to clearly show the difference.
Hello, my name is Najihah. So for task 1 in Python, we generate a clean 10 MHz sine wave and added some noise to create a noisy signal. And then we apply FIR filter. So the result for the SNR will improve from 11.17 decibel into 22.31 decibel. So the plot clearly demonstrate that the filter out closely match the clean wave, proving the filter is effective. So the throughput measure for this Python is 5.82 million sample per second. Move on to task 2. We implement the same FIR filter but using C++. So the SNR result consistent, same as before, same in Python. However, the throughput was lower. It was 2.94 million sample per second. This difference happened because Python used optimized library, while C++ coding used basic loop implementation. With further optimization, C++ can achieve higher speed. Task 1 and Task 2 prove that FIR filter is accurate because SNR is more than 20 decibel, but the processing speed is too low on standard computer. This justifies Task 3 and Task 5, where we will use high-level synthesis (HSL) to make the filter run 10 to 20 times faster than the hardware.
Hello, my name is Faqehah Sofeeyah and I will be presenting both Task 4 and Task 5. So, to simplify our presentation, I've put the Task 4 and Task 5 side to side so we can see clear comparison between both of it. So, Task 5 is basically optimization strategy. We want to hit 50 million sample per second and increase the resource efficiency. So, Task 5 is to maximize throughput, reach the 50 million sample per second while minimize DSP and LUT usage. But there is also a performance bottleneck. Identify the baseline serial execution is too slow for real-time operation. And the technique will be used is HLS pragmas and architectural shift to reduce the initiation interval from 2 to 1. So for task 5, there is a bonus or optional task which is to change the variable from float to AP fix. So we tried it multiple times using variable bit width. 32, we try 48, we try 24. So we try a number of bit width and then the result is the same, which is 5.43 dB. So we call this as quantization noise. This is because the data is very, very small. As an example, 0.012345. So the data is behind the decimal point. So imagine we calculate total number of money, but we remove the cents part. So the cent we see it as small, like 10 cent, 20 cent, but if we accumulate it, it will be a large number. So that's why our SNR is 5.43 because it cannot calculate all of the number behind the decimal point. So that's why AP fix is not a suitable variable and we need to change back to float. So here is the success simulation. So for our throughput, we managed to achieve 100 million sample per second. Our frequency is 100 megahertz, so divided by 1 cycle per sample, so we have exactly 100 msps, and this exceed the requirement of task 5, which is 50 msps. So as you can see here, our SNR is 21.99 dB, which achieved the target, which is 20 dB. Here is the timing for task 5 and task 4. The top one is task 5 and the bottom one is task 4. So as you can see here, the task 5 has lower worst negative slack, which is 5.257 nanosecond, and task 4 have higher worst negative slack, which is 5.906 nanosecond. And both of these is positive. So which means that our 100 million sample per second is physically verified and it will not crash the chip. So it shows here that task 5 execute more faster than task 4. Okay, so this is for design and power, PPA, power, performance and area. So this one is task 5. As you can see, it takes a lot more area. And then it consumes a big portion of the FGPA because we force the chip to run hundreds of multiplier at the exact same time. So our total power spiked to 1.718 watt. So the dynamic power jumped to 1.241 watt and the static power reduced to 0.478. So in task 5, the dynamic power become very big and the static power become very little. This is contrast with the task 4 in the next slide. Okay, so this one is task 4. As you can see at the design part, task 4 use very little area on the FGPA, and then for the power, the dynamic power is very small and the static power is very big, which is contrast than task 5. And also the power is much smaller, which is 0.589 watt. So this is the reality of designing. When we want to increase the we want to shorten the execution time, we will have to sacrifice a little bit with the area and also the power. So the faster the execution time, the higher area will be used and more power will be used. So for this slide, we are going to focus on the LUT and DSP. So as you can see, task 4 use 539 LUT, the bottom part, and task 5 jump the LUT into 30,278. And for the DSP part, task 4 used only 5 DSP, but task 5 used 347 DSP. So in task 5, we use pipeline pragma. This cause for the calculation to do in simultaneously at the same time for faster execution. So if you want it to be done, the calculation at the same time, so we physically built almost 350 individual multiplier for the task 5. So all of the calculation can be done simultaneously. So in task 4, the program focus more on the software part, which is the dynamic power, as we see earlier. But for task 5, we force our program to focus more on the hardware part, to physically build a huge number of new logic block hardware, which help make the calculation done simultaneously at the same time and faster execution time. So in conclusion, pipelining help to make the execution time faster by making the operations done at the same time. But when we want to make something faster, we have to trade off with the area and also power consumption. So the faster the execution time, the higher area will be used and the higher the power consumption will be. When higher area used, the cost will also rise significantly. Hence, when designing, we need to determine which part is more important, faster execution time or lower cost. And maybe we can also settle with something in the middle, so there is a balance between the execution time and also the cost of the design. I think that's all from us. Thank you very much, Doctor, for listening to our presentation video.